Welcome to the Calculus A section. In this section, we'll be dealing with related rates. Now, we're going to delve into further application of implicit differentiations. So, let's suppose we have two variables x and y, which are both changing with respect to time, or t. So, a related rates problem allows us to use one of the given rates of change at any given instant to solve for the other. So let's dive head first into some related rates problems to get an idea of what we're dealing with. So let's say that water is being poured into our conical container that we have here at a rate of 5 centimeters cubed a second. Okay, so the container points directly down as indicated here and has a height of 15 centimeters and a base radius of 5 centimeters. So we're asked, how fast is the water level rising when the water is 2 centimeters deep? So I'm going to write out all of that because that was a lot. So we know that the water is being poured at 5 centimeters cubed a second. We know that it has a height of 15 centimeters. We know that it has a base radius of 15 centimeters, so we're going to actually label this H and R. And we want to know how fast the water level is rising when the water is 2 centimeters deep. So over on the left-hand side, we have a visualization of what is going on. We can see our conical container, and we can see that we have a height of 15 and a base radius of 5, but we do have something called similar cones, which is similar to the concept similar triangles. Okay, so we know that the volume of a cone is equal to V is equal to 1/3 pi r squared h. Okay, and like I said, analogous to similar triangles, we can use the principle of similar cones to find proportions that relate the two cones to find a proportional height to radius. So here we have, let's say, radius, and I'm going to abbreviate that with r, over height. And that is equal to what we have, 5 over 15. So this is a proportion that we have, and we can cross multiply and say that 15r is equal to 5h, and we can also say that r is equal to h over 3. Now that relates both height and radius. Now, we can eliminate r from our original equation, and we're going to go ahead to step 2 and say that v is equal to 1/3 pi h cubed, h over 3, h squared times h. Now, we can simplify this mess and say that v is equal to 1 over 27 pi times h cubed. Now that is the volume that we have for our function. So let's look back at this. In the hidden text, we were actually, it's not hidden, it's just we know that this is 5 centimeters cubed a second is a rate. We are increasing our water level by 5 cubic centimeters, which is a volume, per second. So that means that the rate of that is the rate of the volume with respect to time. So that is dv dt. Additionally, we were told we want to know what the water level is rising at h is equal to 2. So now we have, we should write h W equals 2 centimeters. So now we have V is equal to 1 over 27 pi times h cubed. But what we want to do now is we want to take the derivative of our function, or the d of dt per function. So we're going to say dv dt is equal to 1 over 3 So we're going to say dv dt is equal to 3/27 pi times h squared. And remember, we are taking the derivative with respect to dt, so when we took the derivative of h, we're going to have to say dh dt. Okay. Now that is our related rates equation. So now we're going to plug in all the known values that we were given. We know dv dt is actually going to be 5 centimeters cubed a second. We know that h squared is actually going to be 2 centimeters cubed. And we're going to write that in, 27 pi. Sorry, not 2 centimeters, 2 centimeters. And we also know that dh dt is what we are looking for because we're looking for how fast the water level is rising when the height is 2 centimeters deep. So we can go ahead and distribute all of this, and we end up with 45/4 is equal to dh dt. Now, the fourth step would be understanding what's going on, because problems a lot of the time are going to ask you for specific details that you need. So the question asks for at what step is the water level rising, so it's important that we know that we're looking for dh dt. But if a question asked you at what level is the volume increasing, or at what rate is the radius increasing, for example, if we had an expanding balloon, we would know that the radius would be increasing with dr dt because that's what we're looking for. And we know that the volume of, let's say, a balloon that's expanding, we know dv dt is what we're going to be looking for. So it's really important to understand and listen for or look for what the problem is asking. So I hope that helps, and if you need any more help or assistance, the website has a bunch of problems and assistance. I hope that helps. Thank you.